This paper is also related to soil moisture. There's a truck going by, but that's past. So we are talking about soil moisture in the couple of podcasts before this. So let's continue that thought for maybe one or two more. Soil moisture atmosphere feedbacks have triggered the shift from drought to pluvial conditions since 1980. Okay, what do they mean? It's a pretty strong claim. So what kind of a proof do they offer? Drought and pluvial transitions have attracted widespread attention. However, the dynamic evolution and underlying mechanisms of drought and pluvial transitions remain poorly understood. Here we demonstrate that there is a significant increase in the occurrence of drought and pluvial conditions, so 0.24 to 1.03% per year in terms of a trend over 1980 to 2020 when you look at the global mean trend. We use convergent cross-mapping to detect causal relationships between time series variables in the climate system and find that drought and pluvial transitions can be explained by an indirect transitive causal chain. Specifically, the soil moisture latent heat flux precipitation causal chain is likely to trigger the rainfall following the dryness in humid regions, where enhanced evaporation increases the actual atmospheric moisture, favoring the pluvial occurrence. By contrast, the soil moisture convergence precipitation causal chain enhances the post-drought rainfall in arid regions due to atmospheric circulation dynamics. So moist and semi-arid regions are seeing the drought to pluvial transitions, and they are triggered by soil moisture feedbacks but slightly different ways. Our results indicate that land atmosphere feedbacks play an important role in triggering the drought pluvial shift in a changing climate. Again, I'm going to be brief so you can read up the details and all the nice citations that they use for doing this, arriving at these results. Proposed mechanism for explaining the shift from drought to pluvial from the perspective of soil moisture atmosphere feedbacks. Here, plus and minus indicate positive and negative relations respectively. The colors show the soil moisture latent heat flux precipitation in blue and soil moisture temperature in red, and soil moisture convergence and precipitation in yellow. So those are the feedback loops. Local moisture transport processes, so you can see soil moisture latent heat flux precipitation feedback in the blue, soil moisture temperature feedback in the red, and soil moisture convergence precipitation feedback in the yellow. So here you have the let me read. Local moisture transport processes. Soil desiccation increases sensible heat flux, so exchange with the atmosphere there, and the increasing sensible heat flux further enhances temperature of the lower atmosphere. Hotter air in turn enhances the evaporative demand, and thus latent heat flux is water sufficient. As latent heat flux and temperature rise, atmospheric water holding capacity and moisture content increase, and then you have pluvial is likely to be triggered by the increase in actual atmospheric moisture content. Okay, so see that here. So you have soil desiccation happening, which increases the sensible heat flux, which increases the temperature of the lower atmosphere and its water holding capacity, and the latent heat flux increases the actual moisture content. So you have water holding capacity and moisture itself going up, then leading to clouds and precipitation. Sounds kind of interesting in terms of causality, but how much soil moisture has to be there to actually load up the moisture in the atmosphere to drive pluvial conditions? We'll see that from a couple of reanalysis products which differ greatly from each other, as you will see. What about the soil moisture convergence precipitation feedback? Here again you have the feedbacks happening as Remote moisture transport processes, so atmospheric dynamics. Soil desiccation enhances low-level flow convergence to increase moisture. As moisture in the air rises, pluvial is likely to be triggered, and pluvial prevents further soil desiccation. So ocean is the main moisture source in the remote moisture transport processes. If you are near enough to a coast where ocean is able to provide the moisture, then soil desiccation now, instead of the pathway of sensible to latent heat flux and so on, goes into driving moisture convergence. So you can see that atmospheric circulation impact of bringing additional moisture, evaporation is being shown here, evapotranspiration, and you have atmospheric moisture convergence, which is going to drive clouds and rainfall. Sounds very interesting, right? So they do some calculations. Here are some spatio-temporal pattern of total number of drought and pluvial transitions during the period of 1980 to 2020, and obviously there is a spatial distribution because, as we said, it depends on the arid or wet region in terms of the precise feedback. And then they look at different data sets: ERA 5, GLEAM, MERA 2, and the mean of the three. And the idea is that the results are significant in all of them. So ERA p-value almost 0, GLEAM has a p-value of 0.007, seems quite a bit flatter, and MERA 2 has kind of I don't know if you can call it a regime shift of some sort, but you can always draw a trend line and you can see there are large ranges in terms of the frequencies as well. I won't go into the details, but you can look up. But essentially the argument is that the ideas of drought to pluvial transitions triggered by soil moisture feedbacks are significant in all three products despite the differences. Even if you look at just precipitation products derived from observations, even blended with satellites, they can be different enough that sometimes the transition from dry to wet, wet to dry are very marginal, or they are different enough in the different products that you wonder what is more trustworthy, which product. So they look at the percentage or fraction of areas in the humid transitional and arid regions in three products for the soil moisture, latent heat flux, precipitation feedback, and for the soil moisture moisture convergence precipitation feedback. The main point I would make is that ERA 5 shows a huge moisture convergence feedback in arid regions, and exactly the opposite in GLEAM, but much more amplified in MERA 2. So here the soil moisture latent heat flux precipitation feedback dominates in humid and transitional regions in terms of percentage of areas where this happens, and here pretty much the soil moisture moisture convergence is dominating in all regions here, as opposed to any region with any soil moisture latent heat flux precipitation feedback. There are differences. MERA is much higher resolution. I think I may be wrong on that. ERA 5 also I think has gone to 25 kilometers, so you have to check whether just off the bat whether resolutions themselves can play a role in these things and so on. So obviously you have to keep this in mind when you draw conclusions. So they do discuss some implications. I'm not going to read the whole text of this section. I just picked a few paragraphs. We conduct sensitivity analysis by changing soil depths. By comparing the transitions, drought and pluvial transition frequencies identified by soil moisture in the top and root zone layers, we find that the use of top layer soil moisture is able to capture similar hotspots as well as a significant increasing trend in DPT's frequency compared with those using root zone soil moisture. So root zone soil moisture and the memory doesn't change the impact of soil moisture feedbacks on DPTs. However, the water stored in the root zone layer is directly available to support transpiration and plant growth, which are key regulators of surface evaporation. so there is an indirect impact. Although surface soil moisture responds faster to dryness, the deficit in the root zone soil moisture can directly result in a strong reduction in transportation, since soil canopy re-evaporation and soil evaporation are small. Thus, we identified DPTs based on the changes in the root zone soil moisture instead of the topsoil moisture from the perspective of potential impacts of DPT events. So the evapotranspiration is going to correspond to yields or carbon sequestration, NPP, and so on. So that's a better measure of the impacts of these soil moisture feedbacks on DPTs. This study examines the crucial role of soil moisture atmosphere feedbacks in promoting the occurrence of DPTs over wet and dry regions. We should also pay attention to the beneficial impact of soil moisture atmosphere feedbacks on the hydrological cycle, particularly over dry lands. The reduced soil moisture enhances soil moisture convergence, which partly counteracts precipitation declines driven by limited evaporation. So there is kind of a self-regulation of some sort. In other words, future precipitation changes would comply with the dry get drier paradigm in dry regions without considering the soil moisture atmosphere feedbacks. Due to the existing soil moisture atmosphere feedbacks, however, the increased moisture convergence induced by the decreased soil moisture may partially offset the decline in soil moisture over dry lands, which plays an important role in the global water cycle. On the other hand, the contribution of soil moisture atmosphere feedbacks to rainfall would favor wet get wetter paradigm in wet regions. Although extreme precipitation does not always lead to flooding due to the dry soil moisture modulation of the flood response, the wet areas are more likely to experience more widespread floods due to the occurrence of heavy rainfall after drought. So the transitions and the flooding to follow depend on the soil moisture loading even in the wet regions. So kind of details on the impacts. Finally, our study identifies the critical regions of DPTs and reveals the underlying mechanisms triggering the abrupt transition between drought to pluvial. According to our analysis, using reanalysis data sets, the magnitudes and frequencies of DPTs are enhanced in the regions with strong soil moisture atmosphere feedbacks, which has important implications for advancing understanding of hydroclimatic variability. Our findings can provide meaningful information for policymakers and stakeholders to realize global hotspots that are expected to experience more DPTs in a changing climate. More importantly, revealing the contribution of soil moisture atmosphere feedbacks to DPTs enables us to pay attention to the regions with strong soil moisture atmosphere feedbacks, which will not only support forecasting efforts but also facilitate hazard preparedness and mitigation planning. Well, good information here, but then there are also factors like irrigation, which directly impact soil moisture and hence soil moisture feedbacks. And there are already some debates about whether heat waves are exacerbated by irrigation or they are mitigated, and that will get even more complicated when you consider this kind of feedback to self-regulation of reducing moisture and increasing precipitation and so on and so forth, or in general the drought to pluvial transitions. Okay, so I'm going to leave it there. It's a good paper, so you definitely want to read up in more detail, more carefully than I am doing here, because I just give a brief introduction when the paper sounds interesting. Okay, see you in the next podcast, which will be on, let's see, I have to go back to the directory where I seem to have another paper on soil moisture drought feedbacks, but what is this about? It's the same paper, so I think I just saved it twice because sometimes I forget that I have already saved it. So we'll switch to a new topic now and not soil moisture when we come back. Okay, see you.